Hello again, this is Structural Analysis and Design made fun and easy. This is Structural Steelwork Design to BS5950, braced short column. This is the most simple case, very simple, just get started. So this is now part 5 of 6, a bit more than I've intended. So now we're going to work out what the actual capacity of the column is. This is part 5 of 6. Please like the video and subscribe to the channel, and please donate if you can so I can do more videos. So basically we are now we found out the effective lengths, so now we need to just design the column section. For this question, it's to determine the actual capacity of the UC section in compression. So this remember as well, this one was very simple. This was just actual load only, no bending moment, so makes it life a lot easier. The exam technique, it says 8 marks, so this allows 8 times 1.8 minutes for this question, which is 8 plus 0.8 times 8. Which is 8 plus 8 times 8 over 10, which is 8 plus 64 over 10, which is 8 plus 6.4, 14.4 minutes. Let's say 4 marks, 7.2 minutes for x-axis, and 4 marks for 7.2 minutes for y-axis. Oh yeah, so from the previous parts of the questions, we have LEX equals 6 meters, as you know. LE equals 1 times L for X because it's just held in position, and LEY equals to 5.1 meters. As you know, the second moment, so let's get into this now. We've got the effective lengths, the effective heights, as you know, the second moment of area and the radius of gyration are different for x-axis and y-axis because column H sections are not doubly symmetric, so they're not symmetrical. They are symmetrical about 2 axes, but not doubly symmetrical like a box section is symmetrical about 2 axes. So let's start by looking at buckling about the x-axis. Remember, in this case, all the deflection will be along the y-axis, as we discussed in a previous video. Some of these values are standard obtained for the tables, but for the sake of this video, let's look at them in fine detail. So number 1, we must first of all find the slenderness of the column section. Remember that the slenderness is, I couldn't find the character exactly, but it's lambda, like written lambda. The slenderness is like the same as lambda is effective height divided by radius of gyration, and not forgetting that the radius of gyration is the square root of the second moment of area, or also known as moment of inertia, divided by the area of the section. And so we need to do this calculation for both axes because the values are different for each axis. So let's take the section properties for about x-axis widely available from tables. So they're in the Steel Designer's Manual or online, the online blue book SCI. Tata Steel used to be Chorus. If you can find them online, just Google section property tables. So if you look up, we've got 203 by 203 by 52 UC. IXX equals 5260.0 centimeters to the power of 4. RX equals 8.9 centimeters, and A, area, gross area of the section, is 66.3 centimeters squared. Let's check for learning experience. Let's just do a little check. Let's check for learning experience. The radius of gyration is the square root of IXX over area, so it's 5268 divided by 66.3, so they're both in centimeters, so that's okay. The square root of that is 8.90, so we get the same as the table, 8.9 centimeters. So in this case, x, that is lambda LEX, sending this in the x-axis, lambda x is LEX over RX equals 6,000 divided by 890. Oh yeah, don't forget these are in millimeters. So 6,000 is in millimeters, LEX is in millimeters, so RX is 8.9 centimeters, and that's the same as 89 millimeters. So lambda in x direction is 67.415730, etc., etc. That's the ratio. So basically, from BS5950, we actually have two options. First option, we can use the tabulated values in table 27 A, B, C, D according to the spec of the section in the code as described in table 25 of BS5950. Or it does say in the clauses we can use the equation as denoted in Appendix C to the code. So on doing this, I should have planned it out a bit better, but say this video was originally supposed to be 4 parts, but I think there's a lot of useful content and explanation that people will find interesting. I never really had this explained to me while I was at university, so maybe now I can get the chance to teach students where the teachers didn't do this for me, because this is really essential knowledge. If you don't understand the fundamental principles, sooner or later you get probably going to get stuck on something, because the computers, you can't rely on the PC software all the time. So this series will be 7 parts. So this would be 7 parts. So let's continue with this part now. Method 1 above. So we're going to use the tabulated values in table 27. Let's refer to the code of practice on the screen to find the table, which table to use from table 25. So we got lambda equals 67.41. So 67.41, we have 203 by 203 section. In table 25 it says, oh yeah, so here it is. Can you see that okay? Sorry about the light, but the sun's coming in from the weird angle. So here, table 25, the strut table selection, table 25. So first 3 columns are just type of section. So you've got hot rolled structural hollow section, rolled I section as shown in table 26A, rolled H section or as shown in table 26A, welded plate I or H section, rolled I or H section with welded flange cover plates, welded box section, round square or flat bar, rolled angle, rolled channel RT section, 2 rolled section, laser buttons, compound rolled section, etc. So in our case, because basically we've got 4, because it says use table 27A, 27B, 27C or 27D. So basically suggesting that there are 4 strut curves that can be used depending on the section. So in our case we got rolled H section, that's a UC section. So when it says thickness, that means the thickness of the flange. See note 1. Right, our thickness for the flange is 12.5. Note 1 says for thickness between 40mm and 50mm, the value of PC may be taken as the average of the values for thicknesses up to 40mm and over 40mm. Yeah, so you got, that's like halfway in between. But for us, flange thickness equals 12.5, so we got up to 40mm. So axis of buckling, XX, we need to use table 27B for XX axis and 27C for YY axis. That's in the code of practice. This is BS5950, table 25, strut selection table. So when we go into, so we had lambda equals 67.4, PY equals 275. So here, go across the top, py is 275, which is there. Lambda was 67. Oh, sorry, I'm looking at, yeah, and it should be, H section is table B. That is table A. Sorry, that was a, so here's table B. 275, py equals 275, lambda 67. So you got, yeah, so it says lambda is 66, lambda 68, py equals 275. So for lambda equals, for slenderness 66 is 200, pc equals 210, and for lambda 68, 206. Yeah, so lambda is 67. So that basically means you got oh yeah, it's 207. Lambda, so 210 minus 206 is 4. So that's 2. 66 minus 68, that's 2. So 4 over 2 is 2. So it's adding, if it's lambda equals 67, effect is the PC will be 208. 208. Yeah, 67.4. So let's say 67. So the table PC, from the tables, PC was 208 newtons per millimeter squared. I just got to do that again. Lambda here 67. Oh, you can't see it very well on the video, but if you look at the tables as well, if you've got them, py was 275, lambda 66, pc equals 210, lambda equals 68, py is 275, pc equals 206. So let's say lambda equals 67, then PC equals 208 newtons per millimeter squared. That's for x-axis. So therefore, PC equals AG. So the maximum axial load is the gross area times the reduced stress. So that's 66.3 times 208 newton per millimeter squared. So 66.3 times 10 times 10 times 208, and that gives us, just check that again, 66.3 times 208 equals 130. Oh yeah, divide that by 100, 137.904 kilonewtons. Just to make sure that I've got that right, the maximum actual load, if it was 100% actual, no buckling, P max equals py times AG, 66.3 times 100 times 275 divided by 1000, 1823.5. Whoops, that's not right. Is that 66.3 times 100 times 275 divided by 1000? Oh yeah, so it's 1823.25. Sorry, so 66 for the reduced PC of 208. We got 66.3 times 10 times 10 times 208 divided by 1000. Sorry, it's 1379.04. Yeah, it's always worth checking, isn't it? Because so the PC value is AG times PC, which is 208. So that's 1379.04. So this is the maximum axial load for the column for the x-axis, 1379. So now we just got to do exactly the same thing for y-axis. So let's move on to y direction. From the tables again, oh yeah, from the section property tables, IYY equals 1780. So you can see IXX is 5260. IYY is 1780, so it's quite a lot lower. Oh yeah, this is a bit weird because I got RX from the table, RXX equals 5.2 centimeters, but I think that this didn't quite work out because I did the radius. Let's just do a quick check again. So the square root of 1780 over 52, I actually got 5.8, but I'm not sure. I'm going to check that out. I can just amend the video later when I find out what's happened there, but divided by 52, square root, yeah, 5.85 I think it should be, not 5.2, but I'm not sure what's gone wrong, but I just use 5.2 for now, then I'll try and sort that out in a minute. I just have to amend the video if either I've got the calculation wrong, or the table's wrong, or I've read the table wrong, so I need to check that. But let's say Rx equals 5.2 centimeters. So we already have the value of LEY as 0.85 times L is 0.85 times 6,000 equals 5,100. So lambda y is LEX over RX is 5,100 divided by 52. Oh yeah, because it's 5.2 centimeters, that's 52 millimeters. Lambda therefore in the y direction is 98.0769. So call it 98. So we have a 203 U as before, 52 UC section. As we worked out above, table 25, it says select section, UC, third row down. Thickness means that the thickness of the flange is 12.5. Therefore use table 27C for the YY axis. So we got lambda equals 98. So now we've got to move on to table C. So this is table each. So we got in BS 5950 section 4, you got 2 sheets for each table. Table B takes up 2 sheets. Table A takes up 2 sheets. So A, B, table C, and I just worked out that lambda was 98, wasn't it? 98, that's it. So let's just plug those values in. 98. So we got, this is definitely table C for struts. Lambda equals 98, PY equals 275. Oops, it's there. So PC equals, should be 129 newtons per millimeter squared. Newtons per millimeter squared. Yep, that's right. PC equals 129. I might have to redo this video, I guess, with because of the sunlight, and zoom in a bit on the text because you can't see it that well. But therefore, PC equals AG times PC, 66.3 centimeters squared times 129 newtons per millimeter squared. That's 66.3 times 10 times 10 times 129 divided by 1,000. That's 855.27 kilonewtons. Yeah, just double check this again. Just make sure that it looks right. So Pmax is PYAG, 66.3 times 100 times 275 divided by 1,000 is 1823. So 855.27. That's the maximum axial load about Y. So Y is quite a lot weaker. You can see from that calculation that Y is a lot weaker. It's not quite half, but it's almost, got to say that's more like, what, 5/8 probably. 1379. 855 27 divided by 1359, wasn't it? 62%. So you've got to remember that it's a lot weaker in the y-axis. This is the controlling value then, because the column will buckle in the y-axis. 855 0.27 kilonewtons. So it's not looking, in terms of the question, so that's how you do it, using the tables. That's these tables, table 25, table 27 in BS 5950, using, it's basically clause 4.7, isn't it? Compression members, in BS 5950, compression members, and yeah, so that is that's looking like this column can't resist the ultimate loading of 134i, because 855 is a lot less. Yeah, so that's the answer. So in this was a 203 by 203 52 UC with L equals 6 meters, held in position XX and YY top and bottom, and partially withstand the direction YY top and bottom. LEX equals 1 L and LEY equals 0.85 L. So that's the end of this video. So we've just shown that that's how to calculate the column capacities using BS 5950 using the tables. So in parts, is it part 6? In the next video, we're going to use the equations in BS 5950 Appendix C instead of using the tables. So hopefully you found this little video useful. I found it really useful myself, to be honest, because I haven't really gone over this before and that well, and even at uni didn't know that there was the equations to use in the appendix. And when you're using software, all this is done automatically, obviously, isn't it? So it's just, most people probably don't know this that well. Anyway, thanks for watching. Please like the video if you found it useful. Subscribe, and if you can, donate to the channel so I can do more videos. And see you in the next one. Bye. Thanks for watching.